Now, to conclude our study of polar curves, we're going to look into how to calculate certain areas in the plane where some of the boundaries are given by polar curves. So what is the setting that we're going to be interested in here? We're in the plane. We consider an angular sector. So let's say an angular sector that is bounded by two half rays, theta equal a and theta equal b. And we intercept this angular sector by a polar curve of equation r equal f of theta. And we want to calculate the area that these curves enclose. So how do we proceed? Well, we're going to do pretty much what we have been doing when we wanted to calculate areas or volumes, which is to approximate an area that we don't know how to calculate by the area of something that we know how to calculate. And we're going to proceed as usual, which is to make this approximation, we split the area that we want to calculate into smaller pieces, make the approximation on the small piece, and then as we increase the number of pieces, we get a better and better approximation. So in this case, the way we're going to split, because we're looking at a portion of an angular sector, we're going to split according to pieces of the angular sector. Namely, here the angle theta ranges over the interval from A to B, and we're going to take a pointed partition of the interval AB, just like we did when the interval was an interval for x in the plane. So we take a pointed partition of that interval AB, so we split it into n subintervals, and in each one of these n subintervals we pick a particular value, and that's why the partition is pointed, and that's where we're going to evaluate the function. So specifically what that means geometrically is that we split the angular sector this way, and if we focus on a particular subinterval, that's a subsector, like that, let's say from theta I minus 1 to theta I, that's the interval number I, and we have a particular value that we picked in this, that is theta I star, and we're going to try to evaluate the area of that particular sector bounded by theta equal theta I minus 1 and theta equal theta I, and the curve r equal f of theta. So consider the circle centered at the origin and of radius f of theta I star. You see that this area that we are seeking is closely approximated by the circular sector bounded by our two angles theta equal theta I minus 1 and theta equal theta I, and of radius f of theta I star. So this circular sector closely approximates the area that we want to evaluate, and the circular sector we know how to calculate its value, because here since we know the area of a disk, we know the area of a sector in a disk. Right? If you have a disk of radius r, then the total area is pi r square, and so if you take just a piece of the pizza rather than the whole pizza, the proportion, if the span of the angle is alpha in radian, since to get the whole disk the angle needs to be 2 pi, then to get only circular sector of angle span alpha, then the proportion is alpha over 2 pi, and therefore the area is well, pi r squared that you multiply by alpha over 2 pi, and therefore you get 1/2 r squared times alpha, where alpha is the measure of this sector in radian. So in our case, that means that this blue circular sector has area 1/2 of f of theta I star squared multiplied by the angle span theta I minus theta I minus 1, which we will denote delta theta I. And this is a good approximation of this red sector whose area we are seeking. So now, if we do that for each one of the subintervals, we obtain that A is the sum of these areas of these individual sectors, and each one of them is approximated by the area of a circular sector that is given by 1/2 f of theta I star squared times delta theta I, where this delta theta I is the span of the interval from theta I minus 1 to theta I. But the sum that we have on the right hand side is really a Riemann sum on the interval AB for the function 1/2 f of theta squared. So as we look at all the possible pointed partitions of the interval AB, and as the parameter of the pointed partition goes to 0, the Riemann sums go to the integral of the corresponding function on the interval AB. And therefore we obtain an integral formula for our area, namely the integral from A to B of 1/2 f of theta squared, and we integrate of course with respect to theta. Maybe easier to remember form of this formula is that it's 1/2 integral from A to B of r squared d theta, because of course here we are looking at the case where r is given by f of theta along the bonding curve. So to look at an example, what is the value of the area represented here, where the bounding curve, bounding polar curve is r equal theta, it's a spiral, and we take the part of the area enclosed by this spiral that is shaded in red on this picture. So what does that mean? It's bounded on one end by the polar curve r equal theta. It's also bounded by the half ray theta equals 0, pointing in this direction. That's a blue half ray that now appears on the picture. And on the other side, we're going to bound it by theta equal pi, the second blue half ray. And that should give us our area. So according to the formula we have just established, the area is going to be given by 1/2 integral from 0 to pi of the square of f of theta, which in this case is just theta, so we get theta square, that we integrate with respect to theta. And of course an antiderivative of theta square is theta cube over 3. So we get theta cube over 6 evaluated between pi and 0, which is just pi cube over 6. And that's the value of the area. The unit would be square units, where we fix a unit of length. Now to look at a second example, we are looking at the red shaded area in this picture, where the polar curves, the bounding polar curves, is given by the polar equation r equal 4 plus 3 sine theta. So this is one of the bounding curves, and now the two half rays that bound the angular sector are pointing in the direction of the negative y-axis. We could pick, for instance, theta equal negative pi over 2, and pointing in the direction of the positive y-axis, for instance, theta equal pi over 2. And then we obtain for the area 1/2 of the integral from negative pi over 2 to pi over 2 of the square of the bounding function 4 plus 3 sine theta. And if we multiply things through in this square, we obtain 16 plus 9 sine square theta plus 24 sine theta. That's a double product. Right? 4 times 3 times 2 times sine theta. We know how to integrate 1/2 16, which is 8, and we know how to integrate 1/2 of 24 sine theta, that's 12 sine theta. The antiderivative is going to be negative 12 cosine theta. And so we evaluate 8 theta minus 12 cosine theta between negative pi over 2 and pi over 2, and what remains is 9/2 of sine square theta that we integrate from negative pi over 2 to pi over 2. The way to integrate the square of a sine or a cosine, we have discussed that before, is to use a double angle formula, namely that this sine square theta can be rewritten as 1 minus cosine 2 theta over 2. And therefore what we obtain is 8 pi, which was the value of the function between brackets, plus 9/4 of the integral of 1 minus cosine 2 theta. And now we know how to find an antiderivative for 1, that's just theta, and for cosine 2 theta, that's just 1/2 sine 2 theta. So we obtain this 8 pi plus 9/4 of theta minus 1/2 sine 2 theta that we evaluate between negative pi over 2 and pi over 2. Theta evaluated between negative pi over 2 and pi over 2 is pi. And then you see that sine 2 theta at either one of these bounding values is going to be 0 because sine pi or sine negative pi is 0. So we obtain 8 pi plus 9 pi over 4, which is 41 pi over 4. That's just 2 examples. You will see more examples in your homework. That concludes our study of polar curves, and now you should turn to homework.